Okay, so let me give a short introduction here for our speaker. So Dr. Aaro Jarvinen is a senior scientist in the fusion energy research group at VTT Technical Research Center of Finland. And he's also a visiting scientist in the Eurofusion Advanced Computing Hub of the University of Helsinki. An academic research fellow of the Research Council of Finland, and he's an ITER science fellow. ITER is the big fusion reactor that's being built in the south of France. Very nice environment. And it's a big international project. I'm sure you're gonna talk more about it. And he obtained his PhD from Aalto University in 2015. In 2016, he was part of the Lawrence Livermore National Lab team located in San Diego. Since 2021, his research has focused on applications of scientific machine learning, now back in Finland, but to accelerate the development of fusion energy. So thank you very much, Aaro. What is yours? Thank you.
Thank you. Yes, I would like to thank for this opportunity to give this seminar talk here at CAMITS. And so we will be talking about how to accelerate the development of scientific machine learning. There was already a bit of an introduction, so I think we can go through this relatively quickly. So I've been in about 15 years in fusion energy research. It was 2009 when I did my third summer assignment as an undergraduate student, and I liked it, so I basically stick with the business. And then in 2015, got a PhD and then moved to California, working with the D3D tournament that is located at General Atomics in San Diego. Most of my career, I've been basically working with experimental and numerical research with several of the major fusion facilities like D3D in San Diego or the Joint European Torus in the UK. And then within the past couple of years, I've shifted the focus towards machine learning applications. Now, within the fusion group, I lead a sub-team of 4 PhD students focused on these machine applications. So basically what we do with fusion, in principle, fusion holds a promise of an unlimited source of energy. So what we try to do is that we fuse isotopes of hydrogen, deuterium, and tritium, and the end result is that we get the helium, neutron, and energy. The net energy gain from fusion, you basically need to heat the fuel up to the figure of merit is 100 million degrees or so. And when you reach this temperature, you have to maintain sufficiently high fuel pressure because the fusion power density basically goes up with pressure. And then you need to confine the energy long enough because if you don't confine the energy, it will not exceed the energy that you get out of the reaction itself. So this basically leaves you with this figure of merit triple product that basically applies to any fusion reactor concept. So you basically need to have sufficiently high density times temperature times confinement. Another important part is that in these temperatures, the fuel is in plasma state. So that's why plasma physics is basically very relevant to fusion materials. So let's take a look at how we have been doing over the years in terms of actually reaching those figure of merit values for the fusion triple product. So the largest present day devices can reach conditions near what you would call break even. So basically producing as much energy as you put in. So you can get close to that line, but kind of difficult to get above with present day machines. But the next generation is then projected to actually approach reactor relevant gain. So you can kind of see the development over the years here, where the year is here on the right-hand side y-axis, and then the fusion triple product is here on the left-hand side y-axis, and over the years we've basically been climbing up, and now with the largest devices that we have basically data cloud here close to the break-even line. And you may have seen some of these latest energy records that were completed at the Joint European Torus tokamaks in 2021, and then in the end of last year another energy record. So JET is the device that you basically see here, right? So close to this one. So then getting to the next generation, well, ITER is now the first reactor scale fusion experiment that's being built in Cadarache, France. So here you can see the construction site in June this year. So it's actually proceeding relatively fast. There are buildings and they are actually actively constructing this reactor itself, which you see in a conceptual figure here on the right-hand side. So it's a really big device. This is like the 30-meter scale is given here. I believe there is a human also drawn in the figure. So the major radius is 6 meters, and basically the size of the machine is pretty significant. So this is in linear dimensions. This is twice as big as the joint European tolerance that basically was the largest tokamak until this days. Now here is a tokamak type device, and tokamaks are basically the leading concept they have been the leading concept for several decades in fusion research. But there are also other interesting programs going on. So UKEA in United Kingdom, they have an exciting program that aims to construct a prototype power plant by 2040. But this is based on so-called spherical tokamak concept. Basically, you can already see it here in this figure that what that name stands for is that your aspect ratio is really high. You basically have this spherical shape of the device. It changes some of the properties of the plasma stability and such, which may lead to an attractive value by fusion energy. It also potentially gives you a more compact device. So that's what they're pursuing with this program in the UK, and with a relatively aggressive timescale towards prototype power plants in 2040. So it's really exciting to see this going on. And also at the same time, we have private companies entering this business very actively. So for example, here we have a company that is formed by MIT scientists in Massachusetts. The name of the company is Commonwealth Fusion Systems. Basically, what they are pursuing is exploring these compact devices enabled by development of magnetic technology. So they've raised more than $2 billion from private investors, and they are building this test reactor called Spark in Devens, Massachusetts. And overall, the kind of overarching idea with this is that when you go to high temperature superconductors, you can increase the magnetic field strength. When you do that, you can basically reduce the overall size of the machine, and this can potentially accelerate the pathway to making electrons. So it's really exciting to see this going on, and we're looking forward to see over the next few years how things go. There are also many other companies active in the field, so if you just go to check out the Fusion Industry Association, you can see that there are many companies emerging these days. So overall, when you take a look at this, like the landscape of fusion industry looks very different nowadays than it did 10 years ago. But I'm also really excited to see how things look like in 5 to 10 years time. Okay, now what the tokamak. So basically, tokamak confines the fusion plasma through helical magnetic fields that you generate with toroidal field called plasma current. So the way we minimize the end losses in these vacuum chambers is that we basically twist it into a toroid. So basically, there are no end losses. And in order to get stable confinement, what you need is to have a helical field going through the system. And in tokamak, the way you do it is to generate a toroidal magnetic field with these toroidal field coils. And then you also run a plasma current in the toroidal direction, which inductively gives you this what we call polyidal magnetic field. And when you basically sum the two magnetic fields together, you will get this helical field line that basically twists around torus. And with this kind of magnetic field, we can have a stable confinement for the fusion plasma. And on the right-hand side figure, you can actually see how this looks like when you are operating it. So you can actually see through the plasma because the density is relatively low and the plasma doesn't emit visible light. But where you do see bright light is at the edges where the plasma is touching the wall, because that's where the particles hit the wall structure, they neutralize, and when the neutral hydrogenic particles are flying back to the plasma, they get excited and you see light radiation. And for example, the Bowman spectrum, there are lights in the visible spectrum and you can see those basically with the visible. So now here I have actually a video of how the operation looks like in practice. So basically same type of image that what you just saw in the previous figure. You start with plasma, it's leaning against the wall. And once you have the system started, then you pull this, what you would call the X-point configuration. So you basically have the edge magnetic field steering the diverter like here. And then when we put a lot of heating power in the plasma, the basically very bright, and you can see that in the image. And then a couple of seconds later, we basically ramp the system down.
So the reaction emits photons of different frequencies, visual frequency.
Yeah, I mean, it's like you get actually a wide spectrum emitted by the plasma. The one once you see here is basically dominated by the boundary lines of hydrogen. So basically you have these lines in the visible spectrum. So if you have a visible camera, you can just see those lines. But there would be also basically, there would be spectra in other wavelength ranges as well. We can see that in the spectrum. Okay, so now getting in the topic. So a couple of years ago in the US, there was this workshop organized that was focusing on advancing fusion with machine learning. And even though it's a couple of years old, I think it still gives you a really nice overarching view on what can machine learning do to help various aspects of fusion energy. So I mean, if you are kind of interested to get that overarching umbrella view of the topic, I really encourage you to actually take a look at the paper by Dave Humphreys. But they basically categorized this into 7 priority research topics. So there's kind of 3 in this accelerating science side, which I think is kind of broad, also goes beyond fusion. And then 3 in this kind of enabling fusion side, which gets a bit more technological and maybe fusion specific. And then 1 is just on this kind of fusion data machine learning platform, which is basically something kind of discusses about the platform that if you have multiple devices and research groups all over the world operating with different data sets, how you actually make sure that you keep like provenance tracking and kind of the model version controls in check when you actually try to do this in a globally interacting fusion community. But anyway, if we take a look at these 3 on either side, on the accelerating science side, you kind of can see these examples like, say, accelerating hypothesis generation and testing with like statistical algorithms. Model side, things like just accelerate the models with surrogate modeling schemes, or maybe data-driven augmentation of the models, or in the diagnostic side is that you basically have a diagnostic device collecting data for the machine. And usually what you need to do is to derive some kind of an interpretation of that diagnostic measurement to give the physical quantity that you actually want. And here the machine learning algorithms can basically help us to do more advanced data processing in order to actually draw more information out of the diagnostic measurements. On the technology side, you basically have things like control, which kind of gets similar to, like, say, self-driving cars. And you are basically steering a plasma scenario and collecting information and sensors, and then you want to somehow maximize the controllability and kind of the ways that you project scenarios into the future so that you can make sure that you can steer the scenario. And actually kind of related to the control, there are needs to predict features like the reactor health, or maybe say you want an early warning sign that one of your actuators is about to fail, so then you can actually ramp down the plasma and go and replace that. Or maybe you basically have indications that the plasma scenario is steering into a domain that is potentially disruptive, and you want to basically put in actions to avoid actually running into that domain. And then on the processing side, for many of these devices, and also when you enter the exascale simulations, challenge that emerges is that the volume and velocity of data is thrown at you is growing very, very fast. And you kind of end up in the domain where you might just not be able to just dump it all on the disk and then analyze later on, but you need to have some advanced schemes of actually deal with the data on the fly, or maybe reduce the data so that you actually process the data. So this is also an area that is of interest for the community. So now machine learning on fusion. So when you actually start looking at machine learning applications in fusion and do a little bit of literature survey, you'll find some of these papers that have been published long time ago. So for example, here's an example from 1991, where basically machine learning methods or neural networks were used to extract plasma equilibrium parameters in this device. So there are certain areas in fusion where the fusion community has actively looked into kind of methods to do nonlinear mapping between various parameters in order to actually extract information out of the system. So this is one example. And now, fast forwarding 30 years, there's a study that the EPFL scientists from the Swiss Plasma Center in Lausanne collaborated with Google's DeepMind to train a reinforcement learning algorithm to control the magnetic configuration of the device. So basically, they took a simulation model for the magnetic configuration of the device, and then they trained the reinforcement learning control policy with it and deployed that into the TCD tokamak that's located at Swiss Plasma Center. demonstrate that they can actually control magnetic configuration of the device. So it was a really exciting piece of research that they published 2 years ago in Nature. Now, one area that is probably received maybe the most attention over the years of data-driven algorithms is disruptions in tokamaks. So disruptions are one of the leading challenges faced by tokamak reactors. Like if you have to name one leading challenge, then it's probably disruptions. And basically the point is that the fuel plasma and the confining magnetic field are self-organized to an equilibrium in a tokamak. Now, if you perturb this equilibrium with whatever transient phenomena that may happen, then depending on where you are in the operational space, this may lead to loss of control, a growing instability, and loss of confinement. And as a result, you can get large thermal and magnetic loads on the components. Now, here are some examples of present-day devices. For example, the jet example that you see here. The plasma disrupted the strong inductive electric fields that resulted when you actually have the magnetic configuration just collapsing down, led to acceleration of a part of the electron population in the relativistic velocity. So you basically generate a beam of electrons flowing nearly at the speed of light. And when the beam hits the wall, then you see the melted wall tile. There's an example. And similar type of phenomenon in another tokamak, basically you can see this fireworks in a camera view in the plasma. So basically when the beam hits the wall, then you basically see material being eroded from the wall. Now, in present-day devices, you kind of see these fireworks and localized melting, but when you scale up to reactor scale and the thermal and magnetic energies are significantly more significant than present-day devices, and this can actually cause excessive damage and downtime. It can be really a big issue if you have these events in any significant number in reactor scale devices. But they're also very, very difficult to predict accurately based on traditional physics code. So that's why data-driven methods have been applied by the tokamak community for disruption research for decades. So here you can kind of see some selected references over the years, and kind of what you can see is like every few years there are some papers looking into how to predict disruptions based on data-driven algorithms using the data from devices. Now, the leading challenge, actually I have a couple of examples of this. So here's, for example, one paper where they used a variational autoencoder to basically compress the high dimensional information you get from a fusion device into a low dimensional latent space. And then you can basically project the disruptivity of the plasma into that low dimensional representation. And once you have that system, then you can basically track the plasma trajectory in time and trigger an alarm whenever you basically cross the decision boundary in this low dimensional latent representation. Another example used these recursive neural networks, LSTM units, to basically process the time history of quantities that you get from the plasma device. And then basically the model is predicting that whether you are entering into a disruptive domain based on the history that the algorithm sees from the questions. And then some other examples are using like tree-based methods to basically give a disruptivity scores based on various features in the plasma. Now, one of the key questions still that remains is really the extrapolation gap. So basically the question is how to extrapolate predictions to reactor scale without data at scale. Because I just basically went through the physics that we can basically collect disruption database on present-day devices because the risk of actually causing significant damage is still relatively low. But then we go to these reactor scale devices, and any of these events can actually cause significant damage. So you really don't want to go to the next step, reactor scale devices, and generate a database of disruption. That would be very expensive to do. So actually, you need to be able to predict and avoid disruptions from the first job go. So then the question is how you sufficiently inform the model with physics or learn properties that generalize beyond the training domain. And ideally, the extrapolation of the scale of reactors is conducted well data physics. So here we see some examples. The left-hand side is a model that is intended to simulate the formation and transport of these runaway electrons that basically are in the couple of slides back. And then the right-hand side figure is a model that is basically predicting the nonlinear evolution of the MHD properties of the plasma itself. Now, some of the features that these models have is that they are typically computationally very expensive, but then also at the same time, they are not really complete in a sense. So we have a selection of model parameters that are not well constrained by prior knowledge. So we basically implement often some kind of a phenomenological parameters to avoid actually calculating certain features from first principles. This could be, for example, that we populate diffusion coefficients. We assume certain characteristics from background plasma temperature. Maybe we assume an impurity concentration or impurity profile. And it's like there are a lot of features that we basically give as parameters instead of actually solving them in order to reduce the complexity of the problem. But this also means that we have free parameters. So now, then basically when we do reactor design or real-time optimization or large-scale model validation, we basically need fast many-query inference as well as sufficient and robust uncertainty quantification in order to actually do this kind of work properly. And this is where scientific ML algorithms can be very valuable. So let's go with the validation question. So basically when we validate the model, we need to conduct QQ for the uncertain model parameters. So kind of the common problem statement we have is that given limited resources, this is like CPU or human time, how to optimally quantify the uncertainties. And now here in the middle, we have our computationally expensive model that has some uncertain model parameters. And then whether you are doing the forward or inverse QQ, you basically go from the distribution of code parameters to distributions of predictions or distributions of predictions back to code parameters. And often in the validation exercise, what you really want to do first is that you have some experimental observation that's basically living in this space. So you have some measured feature of the plasma, whether this is total plasma component or something else. And then the question is that can my model reproduce this observable with physically valid input parameters for the parameters that are not constrained. So, however, the models that we deal with, they are not intended to actually propagate in this direction. So basically the inverse mapping that we have is defined only implicitly for the forward. So you basically can pick up parameters in your theta space, and then you take your computationally expensive forward model that is basically a Fortran code or C++, maybe it's modern code, and it can predict the observable in the observable space. So basically the way we do the inverse is that we use simulation-based inference here to establish probability distributions in the theta space given samples of theta. But when we have computationally expensive simulators, we really want to be data efficient when we do this. So basically using the information gained through the previous simulation to guide the search. And this is where, for example, Bayesian optimization is also suited for the test. So here's an example validating the model for runaway electron formation in disrupting plasmas. So here we have a jet example where the plasma is intentionally disrupted with a large impurity injection. There's basically a large quantity of argon just thrown in the plasma to disrupt it. And then this leads to a formation of a runaway beam. So here in this figure, you can basically see time evolution of total plasma current. Current is basically quenching first when we disrupt. And then when you see this plateau, that's because you accelerate runaway electrons to basically take the role of the plasma current. So basically this plateau here is formed by electrons flowing at relativistic velocities. Now, we want to simulate this phenomenon with the dream code. Here we use a fluid model to speed up the throughput of the code. And then the question is that can we actually match this time trace of plasma current with dream? And in the model setup, we have 3 to 8 pre-parameters to optimize depending on how you use the system. So basically you choose like plasma temperature, evolution, argon, assimilation fraction, runaway seed characteristics. And yeah, so this is a work that I published 2 years ago in Journal of Plasma Physics. Now, I'm sure you are quite familiar with Bayesian optimization, but I still have these couple of slides which we can quickly click through here. So basically, BO combines a probabilistic surrogate model for the objective function with an acquisition function for efficient search of an object. So basically, you usually assume Gaussian process regression because this is very efficient when you don't have a lot of data, which is the case if you want the data efficiently. Locate the optimum. And then you can use the acquisition function to basically balance the exploration and exploitation. So in this example, basically I just generate a simple example where you try to find the optimum here. You throw a couple of samples in the domain, then feed the GPA regression to it, and then you can take like an upper confidence bound acquisition function, which recommends the next point of sample. And now you can keep on going and relatively data efficiently have the optimum in the domain. So basically, we took this into the application that I just showed for the dream simulations for jet runaway electron beam formation. And with sufficiently many parameters, 7 in this case, the algorithm is able to find a given agreement. So basically, if I parameterize the background electron temperature so that there's certain time variation with like initial value, final value, and then the time at which the final value is reached, then there's enough maneuverability and resistivity of the plasma so that you can actually find a solution for the time evolution of the plasma current. Okay, this was kind of a nice demonstration that you can do that relatively vanilla Bayesian optimization. But really, for large-scale validation, what we actually would like to do is to go from this case-based to amortized inference. So here's just a figure that I found available in the literature, kind of showcasing the approach. So basically, the previous example was conducting VO for a single input simulation output combination, starting from scratch for each VO task. So basically, doing it case by case. But actually, what we would like to do is to conduct this kind of analysis for a large database of experimental observations. And if you start from scratch every time, then it's very wasteful because you basically repeat very similar simulations for each of the tasks in order to actually find the optimum. So instead, what you actually would like to do in a large-scale application is that you would try to look into ways to amortize the inference over a meaningful operational space. So this actually becomes close to like learning an inverse surrogate for the overall physics model, I mean, compared to traditional surrogate modeling, amortizing the forward. So we tried this year, and here you can see an example of a neural posterior estimation for amortizing the same inference task. So basically, what I did here is that ran a database of 25,000 dream simulations, which is much more than we had in the case-based inference application. But then basically using that database, I used normalizing flow space amortized posterior model to basically then predict the posterior for the code input parameters given the experimental observation. So here in this figure, what you can see is that the black line is the observed current in this jet plasma. So we can give that as a conditioning information for our NPE model. And then the neural posterior estimator basically gives us the posteriors for the three parameters of the model. And now we can then take, for example, the peak value of this posterior and then run full dream simulation and you get the red curve in this figure. So it's basically almost exactly on top of the black curve. Also, because we have this database, we can equally well just train a forward surrogate model. So I basically did that. And the blue area here is basically taking our forward surrogate model and then sampling the posterior that we have here in the RPE. And you can see that that also kind of lands close to where the actual experimental observations. Then the question is that, okay, we had to spend much more simulations to train the model in the first place, so does it generalize? So here just a simple test that I did, I scaled down the runaway plateau current by 25 to 30%, and the model basically finds the posterior for the new target without any additional training. So it's basically very promising in the sense that you kind of have this generalizability within limits to this neural posterior approach. And basically, the research right now that we are focusing on is to develop the methods to train these high-capacity amortized learners within case-based inference workflows. But the basically vision is that when we are doing these inference tasks for various possible scenarios, if we can actually tag this high-capacity amortized learner with that inference workflow, then it can basically learn simultaneously with the case-based inference model. And as it learns a little bit, it can probably be used to inform use case-based inference tasks to faster find the solution. And eventually, if you really have a good amortized learner, it can basically just do the full inference task by itself. So this is basically active research in our group at the moment. Okay, so now, so basically when it comes to the BI with neurofusion advanced computing hub, we have also other Bayesian inference projects ongoing. I'm not going to go through all of them. So basically the examples that I showed are for this runaway electron application. And now we are going to switch gears a little bit and talk about performance. So basically up until now, we've really focused on how to maneuver off normal events in tokamaks and handle disruptions. But then basically the rest of the talk is really about how to maximize the fusion performance of the tokamak scenario. And one of the leading examples of using surrogate models to accelerate predictions in tokamaks is really related to the simulations of plasma turbulence and transport. So here we can see basically the ML surrogate models accelerating high fidelity simulations by several orders of magnitude. So if you want to predict the performance of a large fusion device like JET, for example, here, then really what you need to do is to solve the plasma turbulence-driven transfer. And this can be a very, very challenging computational task. So if you take one of these high fidelity codes here, like the G, for example, and you basically allocate a lot of resources on HPC to simulate this 1 second, you basically wait for a time. Now, the community has developed reduced models for this task so that you actually can simulate meaningful long time scale properties of the plasma. But even these take hours on multiple processors to predict the plasma. So they are still far away from the real-time prediction capability. And then the next level of acceleration that has now happened within the past 5 to 10 years is really surrogating these reduced models with the machine learning methods to kind of get the last bit of speed up, so that now you can basically approach almost like the real-time prediction. Not quite, but it's like you kind of get into the ballpark of very, very fast inference times for these models. Now, when you do this, one of the leading challenges really in training these surrogates is to establish the data set. And this is an interesting study that Lorenzo Giannissi published this year on active learning applied to basically efficiently extend the surrogate models when the full model is computationally expensive. So basically, the idea is that if you have, if you want to generate a training set of million simulations, for example, and your model costs like a couple of CPU hours, then basically you need to invest million CPU hours to do this. And if your model is much more expensive than that, then well, it just basically accumulates in your training CPU hour needs. So the traditional random or basically space filling sampling leads to a serial oversampling and redundant data. So basically what Lorenzo did here, he applied active learning acquisition function based methods to basically data efficiently sample the space. And when doing this for this example case, he was able to improve the data efficiency by a factor of 20. So that's an exciting piece of research, and we're actually applying this now in some of the research we are doing in our team. Okay, now getting into the towards the edge. So basically, here we talk about the transporting the really the core confined plasma. But when you basically have these standard high performance tokamak scenarios in many present day and next day devices, one of the key features that they have is this self-organized deep gradient zone. We call it a pedestal at the edge of the plasma. So here I just have a simple cartoon. So we basically have the plasma configuration here. And then this black line here with the X is the one that is basically separating the plasma that is in contact with the wall, the plasma that is inside basically the confined region. And now basically what you see here is that we are going to plot like 1D profiles, that's plasma radius, and then the profiles will basically be on the y-axis there. And then this dashed line here basically represents this edge of the confined region. So when we operate the fusion devices, fundamentally what you want to do, if you want to reach sufficiently high pressure times energy confinement time for the relevant operation. So this is the triple product essence. The pressure is density times temperature times energy confinement. This was the fundamental criterion for you to have a meaningful fusion rate. But when you actually try to do this, and you heat the plasma, you end up seeing that the profile is stiff due to turbulence. So basically, even if you heat the plasma a lot, you cannot easily change the gradient of the plasma, because all you do is that you just drive more and more turbulence, but the gradient doesn't really change. So your confinement time is effectively going down when you heat the plasma, which is actually would be kind of problematic or reaching the conditions that you need. But actually, what happens is that if you heat the plasma sufficiently, then we see this self-organization, so that if you heat beyond a threshold, then there's a partial suppression of the edge turbulence. And this basically means that you can establish steeper gradients at the edge. And now what happens is that you have this steep gradient zone that we call pedestal, that basically now elevates your entire core profile to much higher values. We call this H mode, standing for high confinement mode operation. And basically, this is the basis of most of the standard high performance scenarios that we have in fusion devices. But then actually trying to predict the physics of the pedestal, it gets relatively convoluted. But here I have a video to show like an example pedestal formation at JET. So basically what you see here is electron density measurements with the high resolution Thomson scattering diagnostics in the plasma. So basically get an electron density profile in this location. And then you can, oops. So you can see that when the heating power goes up in this point in time, then there's a steep increase in the gradients at the edge. So it's right about now when the heating power comes in. And there we go. So you kind of see this significant transition from the low density range to the high density range. And but when you actually then try to predict the physics for this region, an actual high fidelity pedestal model would be multi-physics, multi-scale, which means scientifically very, very challenging and computationally very expensive. So basically, the kind of components that we need to model a pedestal, we talk about MHD, which stands for magnetohydrodynamics. So you kind of have these macroscopic stability features of this edge steep gradient zone. And then you have the transport properties that you would basically model with the turbulence codes. And these are then coupled to what's happening in the plasma domain outside this confined region where you basically have plasmas in contact. So you can see that the kind of the interdependencies can get very, very complicated. And often what we do in field of fusion is that we reduce the complexity quite a bit, so that we basically say that there's basically an ideal magnetohydrodynamics limiting the stability, and then you assume simplifying assumptions about the transport, and when you constrain the two, then you can basically estimate what the pressure is on top of the pedestal. But now this is actually where our team at VTT started to focus quite a bit. So our primary focus is really on trying to facilitate this tokamak pedestal modeling with machine learning. So basically trying to go after some of the reductions that we usually apply in the fusion community in order to actually have higher fidelity reduced models based on machine learning surrogates and data-driven models. So we have part of the team members are looking into machine learning accelerated models for the MHD stability. So this is basically looking at the macroscopic stability properties for the edge. And with surrogate modeling schemes, we basically can get very, very fast inference for those. Some other part of the team are looking into accelerating the transport models. And this is actually the project that brings me here, for example, today. And then we have basically team members looking into how to use experimental data to learn features not represented by the feature. So basically trying to represent the reality gap. And starting with this reality gap models first, because this is the one that we actually got started first in this domain. So we looked into state representation learning algorithms for generic state inference in fusion plasmas. So there's a review paper in neural networks a couple of years ago that really kind of piqued our interest a few years ago. And then basically our vision is that these algorithms can be quite useful to learn to represent the reality gap from database of experimental observations and simulation results. So the way we've done this, we've basically explored this representation learning for present-day tokamaks. So taking a look at the large database of measured profiles, it's like several thousands of plasmas, learn a low-dimensional latent representation, and then from this latent representation, you can then generate predicted pattern profiles. And we've been doing this with variational outline encoders, which I'm sure you are familiar with. So basically, we project the high-dimensional observed data into a low-dimensional latent space as a distribution, and then decoder basically brings us back to the full-dimensional state. Now, we can do this with the data, and the question is that how do we connect the machine control configuration to this picture? Because right now we are just consuming observables and producing observables. And the way we decided to do it is just to go basically with this kind of a domain invariant variational outline encoder type structure. Basically, by attaching prior and auxiliary regression components to the model, the intention is for the algorithm to disentangle the various scenarios. So this is a paper that my PhD student published last year on kind of our first proof of principle tests on this. So the idea is that you basically now have this standard stochastic part of the Latin space, but then you basically have these auxiliary units giving you a regression from the machine parameter configuration into part of the Latin space. And you're basically telling the algorithms like, I want the Latin space to be structured in such a way that different scenarios are disentangled in different physical locations of the Latin representation. And when you do this, now you can actually then take the model and generate pedestal profile based on machine control parameter configuration. So you can basically give machine control parameters as a conditioning input that gives you a distribution in Latin space, and then you can sample from that distribution, and through the decoder you get basically predicted pedestal profiles. For example, in this example, you see that when we have plasma current from low values to high values, you see the density increasing strongly, which is actually consistent with what we often see in these fusion devices. Now, the next step after that was to then explore this for a multi-machine database. So what if you take two devices with different spatial dimensions and you try to learn like size scaling properties in the Latin representation? So I basically took the same model structure, but now I actually dedicated this one Latin space unit for the machine size itself. And then the question was that, how does the algorithm actually choose to deposit the information in this part of the Latin space that should scale with the devices? And doing this with the databases, here are the results. So basically, you can see a 2D cut of the Latin space, and the color contours here show the inferred size of the device, and then the other color contour shows the inferred pedestal drop density. So basically, these tags here are the values that I get from the regression model. So I basically, when I give the machine control configuration and the device size, then I basically get this conditional distribution in the Latin space. And then basically from this conditional distribution, I can now sample and predict what the profile should look like. And you can see the comparisons here on the left-hand side for JET, which is this case, and right-hand side for Aaro, which is this point. And the red shaded area is basically decoding samples from those distributions that we have in the Latin space. The black dots are basically the experimental observations for those specific plasma discharges. So it's very, very exciting. Also, another feature that you can see here is that when we increase the machine size but keep most of the other parameter constant, the pedestal density is going down, which is actually consistent with what we've seen, this kind of a Greenwald-like density scaling in fusion plasma. Now, one more thing that we did with these algorithms was to try to learn dynamics from the databases. So basically, by pushing the Latin space out regressively and then comparing the Latin representation to an encoded state, we can basically generate a loss function with a forward model and try to basically make the model have the capability to predict like dynamics in time. So the way we do this is that you basically train everything within a single computational graph. And the idea is that when you jointly learn the representation and the dynamics together, you basically give incentive for the algorithm to organize the representation in such a way that it basically is easy for you to predict dynamics as well. So when you basically do this, here's an example for Aztec substrate. So you basically actually see pretty promising time evolution prediction performance. So based on the machine control parameter configurations, you can see the true densities and temperatures here, and then basically the predictions with the forward model here in the lower panel. So basically the algorithm is able to predict reasonably well the time evolution of the plasma scenario given machine control parameter configurations and their evolution time. However, if you actually give a plasma out of the training distribution, then the predictions diverge from observations. So here, for example, the model is predicting temperature increase in the domain with the heating power increase, which is kind of makes sense, like more heating power, more temperature. But actually what happens is that there's a temperature reduction in the real plasma because of impurity accumulation. Our model doesn't know about that. So basically, since it doesn't have access to the relevant information, then it basically has no hope of actually predicting that the temperature is actually going down because the impurities contaminate the plasma and because of a lot of radiation, and the radiation plus the plasma. Now, basically all those were just based on pure data from experimental fusion devices. But really what we are kind of moving towards is this trying to learn a joint representation for both observations and prior physics models. So basically trying to encode the reality based on observations. And here is a simple study that I did this summer. So basically taking published experimental and simulation databases from these two papers and then pulling them together into the representation learning algorithm. And then generating like predictions that asking the algorithm, okay, generate predictions as if this was observations or simulations, and what kind of characteristics do you see? And you can basically see in these two dilatant space cuts that the general trends are kind of similar between the two, but there are some on absolute level, there are discrepancies between the two, as you would expect, because the simulation is not perfect. And it's kind of a first proof of principle in this domain, and we're kind of moving more and more into that direction. And actually, to enable this, in this year, we started the surrogate modeling projects for pedestal MHD and transport. So basically, on the MHD side, we have a Eurofusion project going on this and next year to surrogate linear MHD stability properties. And then on the pedestal transport side, we basically been working this year on this work on surrogating the linear gyrokinetic stability properties or the pedestal plasma, and then working together with the collaborator to try to basically come up with data-driven accelerated factory. So basically on the linear MHD side, what we basically are, the key challenge that we have is that you have a numerical predictor, numerical model that basically predicts the decision boundary in the operational space. It's like, is it stable or unstable? And you really want to get that mapped accurately, and it seems to be a bit of a challenge. So actually what we plan to do here is to use these kind of active learning methods like what Lawrence published in Fusion to more data efficiently actually map this boundary. And this work is ongoing. The PhD student working on it. And then on the pedestal transport side, we basically now done our first proof of principle test on just taking like a simple model set with a couple of different dimensions, generate an initial data set and trying to fitting some machine learning surrogate models to it to basically demonstrate that we can do this. And now we are basically moving towards the next step with actually coupling this with the experimental data from fusion devices. And that actually brings me then to the end of this talk. So fusion energy provides really an exciting and versatile environment for machine learning algorithm development. It's also a potential source of unlimited clean energy. And now, basically, what we have here is that the laboratory experiments provide large quantities of data for very complicated self-organized phenomena that range through a wide spatiotemporal scales and temperature ranges. And this is really a great challenge for scientific camera as well. And well, machine learning has been applied throughout the years for various areas, but there's still a lot to do in this domain. I would encourage collaborators also kind of getting excited about trying different methods. And yeah, finally, check out our GitHub page on Jarvinen Surrogate so you can find it online. And yeah, if you want to contribute, just reach out to us.
Questions? Other questions? So, you know, obviously, the goal is to come up with accurate surrogate models and, you know, solving these problems, you know, all of that stuff. And then you're gonna need, of course, a lot of data to train this. And you mentioned that. And, you know, some of these simulations could take literally years, as you said. So, so then why not use experimental data? I mean, can we actually fill in this gap with a lot of experimental data?
For present-day machines, we to some extent can. I mean, in principle, if you have a lot of data from a present-day machine, then you can kind of do interpolations. And basically, it's kind of what we showed already with, for example, these examples, that if you have data, you can train the model and be able to interpolate. The real challenge is that actually what we really want to do is to predict the next step vectors where we don't have data yet. That's why you need the physics models to actually bridge the gap. Of course, it is potentially also possible that you start the new devices and during the commissioning phase, you just can keep on training the model like on the fly as you get more and more data. The challenge there is that if you kind of take that approach, then you cannot really extrapolate too far beyond where you have data already to not increase like the risk of actually entering a domain that could like be potentially dangerous. So it's like the way I see it is that the most likely kind of the best fitting path forward is to kind of try to do the hybrid as much as possible. Like try to bring in the physics that you do know into these models. And of course we have the data available, so we should also augment the models. And this is also like something that machine learning algorithms actually give us the means to do, while trying to do this with some kind of heuristics based on top of physics simulations seems like it would be much more difficult.
Absolutely, but even for present-day machines, aren't you interested in predicting, let's say, the onset of disturbances? In which case, you showed an experiment where you actually create a disturbance,
yeah,
and you get the data. So that is purely experimental data, right?
Yeah.
So I mean, like I said, the physics is very complex. Yeah. And you may not actually know all the physics, right? Yeah. And so it seems that machine learning could present an opportunity here to discover perhaps new physics, yeah, or even bypass the physics, yeah, completely. So I don't know how appreciated such an approach actually is in the community, but
I think it is. There is kind of course, part of the community is like you should just basically go with like physics predictions and accelerate those. But I mean, I would say that the community acknowledges there's value in both. It's like you just basically use the tools broadly to advance the fields in whatever you
can. It's a purely data-driven approach in that case. Yeah.
Yeah. But I mean, for example, I think the most purely data-driven approach on this slide set is really this representation learning work that we have done in the past, because that's just data-driven. It's like there's relatively little physics constraints given. I mean, maybe we have something like inductive bias in the algorithm design to stabilize systems. So you basically make sure that if you predict like densities and temperatures, and you try to also make sure that the pressure is concentrated as well, because you kind of know that
it's not completely data-driven. There is some, yeah, absolutely.
You kind of try to design the algorithm so that it's easy to learn the representation of the data that you want.
Yeah. It's interesting. Other question. Okay, so let's thank Aaro again. Thank you.